Good afternoon, everyone. My name is Alexandre Pombo, and today I'm going to present my work imitation game. Proca Stars that can mimic the Schwarzschild shadow. This work was done together with Professor Carlos Herdeiro, Eugene Radu, Pedro Cunha, and Nicolas Sanchez Google. With all the new observational event horizon telescope like evidences, one question arises. Is the shadow really an evidence for a black hole? Well, typically, the shadow is associated with the presence of a light ring and the illumination source, in this case, the Christian disk. Light rings have been shown to be a generic feature of stationary black holes and to have an important impact on the ring down shadow. So, therefore, it is generically assumed that an object to mimic these black hole shadows must possess a light ring. So, what we should really ask is if a dynamical robust horizonless object mimic a black hole. And what we mean by these horizonless objects is boson stars. As it was already extensively explained, a boson star is an hypothetical astronomical object formed out of bosons. For these stars to exist, one needs a stable boson in nature. Compact boson stars are usually studied involving massive complex scalar fields with a U1 global symmetry, and they may be described as an everywhere regular lump of scalar or vector boson. In addition, boson stars have been proposed as possible dark matter candidate objects. In this case, they will interact very weakly with the electromagnetic radiation and be essentially invisible. However, due to the immense gravity of compact boson stars, they will be able to bend light and, in a binary system with a normal star, even create an accretion disk. Now, but the question is, can a boson star be a black hole mimicker? Well, if the source of light in the vicinity of the boson star has the same morphology as it will have around the black hole, then the observational image could be the same. In other words, for a boson star to be a good black hole mimicker, both the source of light distribution and the way that light bends must be the same. For a black hole shadow, a key feature is the cutoff in the emission due to the disk's inner edge, which is determined by the innermost stable circular orbit of the black hole, or Axion. However, for spherical boson stars, there is no Axion. There are stable circular orbits all the way to the center of the boson star. So therefore, we do not have this scale, and in principle, the image cannot be obtained. So it is clear that boson star should not have the same image as a black hole. However, recent developments in general relativistic macro-hydrodynamic simulations have shown that the angular velocity of the orbits omega attains a maximum at some radial radius r omega. In this work, it was suggested that r omega determines the inner edge of the accretion. In fact, the authors even shown a boson star with the same structure of the accretion disk as a spinning black hole. However, in this work, the boson star is in the stable branch. So, it seems possible that boson stars are black hole mimickers. However, can they be dynamically robust? So, the objective of this work is to assess if stable and dynamically robust boson stars can yield the same shadow as a black hole. To do this, let us consider the Einstein matter action where the matter field is linearly coupled to the Einstein gravity. And for the matter Lagrangian, considering the scalar field, we consider that it is under a self-interaction potential below phi, and for the vector field A, it is under a self-interaction potential V of A squared. For the magnetic ansatz, we consider the unusual spherically symmetric metric ansatz. Considering the scalar field phi, and the vector field A, we consider that they have an harmonic time dependence. Now, in terms of the self-interaction potential, the simplest case is just the master, which in fact is not a self-interaction, but we will consider it in the potential form. Then we can have a quartic self-interaction and a 6-6 self-interaction, where this later is known as Q ball or the Q star because this potential is known to yield Q ball solution. In addition, we can also study an Axion-like potential, which for small values of the scalar field is very similar to the one of the polynomial self-interaction. However, as we increase the value of the scalar field, we observe a divergence on the behavior. And even we observe that the Axion potential has a periodic or oscillation behavior, which can yield solutions that are not asymptotically flat. For the vector field, we'll consider just the meaning and the self-interaction. Now, in the solutions, the numerical solutions were obtained using an in-house developed parallelized adaptive step input the method, where all the solutions were obtained using the virial identity that João Oliveira has shown. Now, what is left is for us to see if these Boson-Stars solutions have or not Black rings and Scalar orbits. For this, we observe that the radial geodesic equation for a particle along Boson star is given by the following formula, where E is the particle's energy and L is the particle's angular momentum. K is a parameter that labels in the null and unlike geodesic. For a circular orbit, we must impose that both the radial velocity and radial acceleration are zero. With this, for the null geodesic, we obtain the following equation, where we can observe that the condition is only metric dependent. As it was shown, Black rings always comes in pairs, one stable and one unstable. However, we wish to find the first Boson star solution containing a light ring. In this case, both the light rings are in the same place and they are degenerate. In other words, what we wish to find is the first ultra-compact Boson star. Concerning the time-like circular orbits, the angular velocity omega along these orbits is again only background dependent, as expected. And as already mentioned, Boson stars do not have an ice. However, an accretion disk may have an inner edge even around these Boson stars without an ice core, which occurs if the angular velocity along these time-like circular orbits contains a maximum at some radial distance, where this r omega, the radial distance, corresponds to the scale of the inner edge of the accretion disk. Now, the two remaining questions are if these solutions possess the similar scale and if they are in the stable solution. So, to study the first, we'll consider the ratio between the R of ice cone and R omega of the Boson star and the Black. However, concerning the latter, if the solution is or not in a stable branch, we can observe the domain of existence of the Boson stars, where we have the ADM mass as a function of the scalar field frequency. And what we observe is that as we go inside the domain of existence spiral, the stable branch goes from the maximum scalar field frequency, or the field frequency, as we'll see ahead, until the first maximum of the mass. And then, after, we only have a stable solution. And as you can see, both the ADM mass and the field frequency undergo oscillation. Therefore, they are not good parameters to uniquely label the solution. However, the field amplitude at the origin goes monotonically. So, it is a parameter that uniquely labels the solution, and you can use it to see if the solution is or not in the stable branch. Now, let us study some numerical results. First of all, I would like to point out that for all the solutions that we studied, unfortunately, the first ultra-compact solution is well inside the domain of existence spiral. This means that there is no ultra-compact Boson star solution. And therefore, the only chance for us to have a true black hole mimicker is if this inner edge of the Christian disk is in the stable branch. So let us start by the simplest mini Boson star case. In this case, the first solution containing an inner edge of the Christian disk is far from the stable branch. However, if we add a quartic self-interaction, in fact, a positive quartic self-interaction, what we observe is a tendency from the solution to the stable branch. If we then add a 60th term, we observe a similar behavior. However, observe that since phi is always smaller than 1, this 60th term has a smaller impact than the quartic one. So therefore, we are not expecting that an increase in this 6th term will have such an impact as the quartic one. Even though the previous analysis show that the simultaneous increase in both the quartic and the 6th term can yield some interesting results. And so that's what we did. We choose the two highest values for which we are comfortable with our numerical computation. What we observe is that the solution indeed tends to the stable branch. However, our omega is terribly fairly below the I-score radius of a comparable black hole. Therefore, the solutions, even though they can or they seem to be able to, they still have long bond to do. Concerning the Axion scalar, for large values of the Axion coupling, we observe that the solution is very similar to the one of the mini Boson star. However, if we further decrease the Axion coupling, we observe an emergence of a second maximum of the mass in the domain of existence, and with this, a second stable branch. And with this stable branch, in fact, we can obtain solutions with an inner edge of the Christian that are both energetically stable and dynamically robust. However, they do not have the right scale. So maybe if we further decrease this Axion coupling, we are able to have solutions with desired properties. However, again, this starts to be computationally demanding. So the only hope is for the Proca star. Well, for the Proca star, we have a completely different behavior than before. As we go inside the spiral, the domain of the spiral, what we observe is that our omega comes from a very high value down to 0. It then stays at 0 and then has a second transition for positive values. And this second transition that we have observed in the scalar field Boson star. In this case, the solutions are never in the stable branch and never have the exact scale. However, for the Proca stars, this first branch that is absent in the scalar Boson star is always in the stable branch. And since this comes from a very high value down to 0, it is easy to find a precise solution with R omega equal to the R of I star. And so what is left is for us to study some shadow. Now, for the shadow, we have two configurations. First, we can look perpendicular to the Christian disk. In this case, what we should observe is the Christian disk with the inner edge and the shadow inside, which is exactly what we observe for the black hole. The Christian disk and then the inner edge with the shadow. And in fact, even though there is some difference in the scale, is exactly what we observe for the Proca star. The structure is the same. We have the Christian disk and then the inner shadow. Then we can also observe parallel to the Christian disk. In this case, we should observe the Christian disk, the shadow of the object, and then since the black hole has a gravitational pull strong enough to bend light, we should observe a halo surrounding the shadow. That is from the light that is emitted from the accretion disk behind the object. So, which is exactly what we observe from the black hole. The accretion disk, and then the halo surrounding it. However, for the Proca stars, since these solutions are very diluted and are not ultra-compact, they lack the gravitational pull to bend light. And so we do not observe the halo from the light that is bent behind the Proca star. And this creates a distinguishable characteristic between these Proca stars and these black holes. So, what we conclude? First, models with dynamical robust spherical boson stars can mimic the shadow of a Schwarzschild Black hole. In fact, in the case of spherically stable scalar boson stars, while the polynomial self-interaction cannot easily solve this issue, the axionic model may be able. On the other hand, for spherical Proca stars, we found that even the simplest model can indeed mimic a Schwarzschild Black hole. And even we remark that despite the magic between R omega and the ice of the black hole, the lensing analysis reveals a slightly different shadow. However, since R omega varies from a large value continuously down to zero, a precise shadow of the degeneracy will be achieved. And so, more importantly, our lensing analysis reveals that the degeneracy only holds under certain conditions. So, can a dynamically robust horizonless object mimic a black hole image? Well, yes, but only under certain observational conditions, which curiously are the same as the M80 star event horizon telescope observations. Thank you.